Right. Easiest. You get two tabs. You have two windows, not two tabs. And each one is things. But where is it?
Okay, good afternoon, guys. Today we will meet a new person, Adam. You remember there is optimization method which is in Torch, which is called optim.adam. So today we will talk about optimizations for neural networks. And I opened Zoom to record the lecture because I didn't do this with the previous class. So our topic for today, optimization for neural networks. And let's recall the problem. We have a function which is the sum of, like loss function, which is the sum of individual functions fi. And because it's more mathematical problem, I'm using X instead of W. Typically, we use W for weights. Now we just will consider arbitrary function of X. And we want to, for example, minimize this function with respect to X. And the algorithm that will know is gradient descent. Every new point, again, I will use a different notation today. The subscript will denote not the component, but the time step of iterations. Xt is represented as xt minus learning rate. And instead of eta, I'm using alpha. So different, will be different notation. Alpha times gradient of f. So what is the time complexity to evaluate one function f let's say the computational graph contains m nodes. What is the time complexity to evaluate individual function? It will be O of m. What is the time complexity to evaluate the sum, the f, the complete or full batch loss? N times n, yes. To evaluate f, the time complexity will be m times n. And if we have, for example, 10,000 data, then it will be m times 10,000. If we have million data, it will be million times. So what is the time complexity for the gradient of the full batch? It will be the same if we use back propagation. If we use forward mode, it will be also times the number of the dimension of x. And as you remember, our first more efficient algorithm was stochastic gradient descent, where we sampled randomly index I. From uniform distribution over n points. And then our update rule used only one term from the sum. And what is the time complexity to evaluate this algorithm? What is the time complexity to sample one random number? How numbers are sampled in programming languages. There's seed. So it's a looked up table, so it's a constant time. And the time complexity to evaluate the gradient of function will be all of them. So instead of evaluating the full batch gradient, we evaluate only individual function gradient. And then one step of gradient descent is much faster than using full batch. The next modification was mini batch. Mini batch. So in mini batch, we sampled several data points. We sampled several indices. And then the update rule looked as follows. So average over batch size. Sum for, let's say, k. F index with index y ik gradient. And the time complexity for this algorithm is big O of m times b. Let's look at the example. So let's say our function f. Now I will use w because I will talk about linear regression. F is 1 over n. Sum of the squared residuals wx I minus target squared. And let's plot this functions. So this individual term fi is a parabola. With respect to w. This is w. And here is our function corresponding to the first data point, f1. Then we have another function, f2, maybe in different order. Then we have another function. Maybe they can coincide, f3, and so on. So we have individual terms. And what is the sum of quadratic functions? Will it be a linear, quadratic, cubic function? What is the sum of quadratic functions? Quadratic. Yes, so the sum of the f will also look like a parabola. So the sum of these functions, or f capital, will look something like this. So this is our full batch loss function. And the goal of our optimization procedure is to find the minimum of this red function. So let's start and choose randomly W0, and my random choice will be the 0. So I will choose W0 as at the origin. Then I should choose randomly one of these functions, f1, f2, or x3, and calculate the gradient. So what will be the gradient of f1 at 0? So f1, if you continue this function, it will intersect somewhere our y-axis, and you can calculate the slope at. So will it be positive or negative? Negative. What about f2? If we calculate slope of f2, it will be negative. So for any function f lowercase, the slope here for gradient will be negative, and because we use negative gradient, we will move into positive direction. So the new point doesn't matter which function we will sample. The new w1 will be here somewhere to the we move in positive direction. So we're approaching to the minimum of our target function. What about this point? What will be the slope of w1 for any f? It will be again negative. So the new point will be also we will move to the right. W2. And next point, again, all the slopes will be negative, so we will move to the right. Doesn't matter which function we choose. But here, now, we have a different outcome. So now if we choose function f1, the slope for this function will be positive. So if we choose function f1, so then the next point, next w value will be in negative direction. If we choose function f2, so if we choose function f2, the slope for this function will be negative, and we will move in positive direction. So now the position of the next weight, updated weight, depends on the choice of the function. So this region where the direction of the gradient depends on the index of our function is called confusion region. Because depending on the choice of I, we will move to the left or to the right. And when we reach this confusion region, then it's a good idea to use smaller learning rate to avoid like large jumps to the next point. Maybe we just used not good index for current update step. So and also it means that if we use stochastic gradient descent, we will never actually reach the true minimum of the full batch loss function. But in practice, stochastic gradient descent results in better performance on validation set. Why it's the case? Why the full batch minimization, when we find the weights which minimize this complete loss function, is worse than to find a weight somewhere in the neighborhood of this minimum. Do you remember overfitting? So if we find the minimum of our complete full batch loss function, then we will fit nicely training data. But we don't know other data types that we didn't see during training. So maybe it's not the best actually parameter in that's called overfitting. So gradient descent also helps to avoid overfitting problem. That's why in practice it's not only computationally efficient, but it also results in better model estimation. So now let's talk about how to reduce the learning rate alpha. Of course, you can use some what is called scheduler. In the Torch, there is also module scheduler, and you can choose different options. The standard choice is, for example, to decrease your learning rate, for example, by 10 after, and you indicate which number of iterations. For example, after 5 epochs, we will divide the learning rate by half or by 10. It's called constant, piecewise constant decay. So Or you can use 1 over n, where n is the number of epochs, or 1 over square root of n. But maybe it will too fast decay, and your learning rate will get very small, and you won't update weights efficiently. So if your function is very nice, like convex function, as this convex as parabola, um, then there exists a numerical method, which is called Newton's method. uh, that actually um, adjusts this learning rate with every iteration. Some function here and gradient. Is anybody taking the computational math courses? Okay, so because this is the standard iterative algorithm for to find the, for example, zero of the function, the roots of the function, or if you use instead of function gradient and you find the zero of gradient, then it's optimization algorithm. So here we should use the matrix of second derivatives. It's also called Hessian. Um, but sometimes the following notation is used, kind of double gradient, and the Hessian matrix is just the matrix of partial derivatives, second order partial derivatives. Uh, with respect to x1 twice, with respect to x1 to x2, and so on. If you have the dimension d, then sorry, it's a little bit abuse of notation because here my indices are the components, and here the indices are time steps. But I hope you understand that I mean by this matrix, just the matrix of second derivatives. So this is the first line. The second line will be a partial derivative with respect to x2, x1, x2, 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 x3, and so on. So we have matrix d by d. So this matrix will be d by d. And then we should find the inverse matrix. So for quadratic function, for parabola, this method will converge in one step, in one iteration. Because quadratic function has only two terms in Taylor expansion. And if we use the second derivative in our method, then we actually use all the information about this parabola function. So I just want to say that there is an algorithm that adjusts learning rate automatically. Because this second derivative is calculated at the current point. The problem with this method is to invert the matrix. If your neural network has, for example, several thousand parameters, this is very small neural network, then this matrix will be 1,000 times 1,000, and there is no algorithm that can invert such matrices. So people discovered an algorithm not a long time ago in 2010s how to approximate this. And currently there is a lot of research how to approximate the Hessian matrix instead of using the exact matrix of second derivatives and inverse. How to approximate this still to update this learning rate with new iterations instead of using just constant or 1 over t, for example, learning rate. And the first method that we will talk about, which is modification of vanilla gradient descent, is called stochastic gradient descent with momentum. Stochastic gradient descent with momentum. Also, it's called with inertia. And Rose, I prepared 4 slides for you for today. The derivation of this method from the first principles, because last time we talked with Rose and he had this vision that machine learning is just passing bunch of data in a neural network and then get some result without accuracy estimation, without kind of guessing, so without some actually say proved expectations from the algorithm. And so that's why I prepared one illustration how this method that we will talk about was actually derived. And I hope you will appreciate, I'm not sure about other students, all the math behind that. So, and also just talking about this opinion that deep learning is kind of just using a bunch of data and getting result. You've heard about the phrase garbage in, garbage out. So in machine learning, you can use a nice data set, but you can use a garbage model and you will get garbage out. So in this case, you should choose a model that actually will provide the expected result to choose a good model. Okay, so it's not philosophy. Let's talk about the method. So first, I will give you intuition, how this method is typically taught in optimization classes or machine learning classes. But then I will actually provide, of course, I won't derive. I just spent several hours last night to write all the math, so I will just show the slides. So the method itself, the update rule looks as follows. It begins as gradient descent, and let me use just constant learning rate alpha without subscript. Mm. And I'm not using the subscript for f because f can be individual function, f can be mini batch, f can be the full batch. So just arbitrary function, we minimize arbitrary function f. So this looks like this normal gradient descent, but then there is additional term which is called inertia, beta times xt minus x on the step t minus 1. So let's look how this additional term changes the optimization process. So let's say we have the level curves of a loss function. So you remember our function looks something like that. And level curves are the curves where the function has the same, takes the same value z. So this kind of the view from above, from the top on this function. So the minimum is here, and on each like larger ellipse, we have larger value of our loss function. And let's start with a point, 1 point x 0. As usual, you can see this point was chosen randomly by me. So then our next step, because we don't have the point with index -1, will be just a long gradient. And gradient is always perpendicular, anti-gradient, perpendicular to the level curve. So this will be our first point x1. Then if we use vanilla gradient descent, then the next point would go in this direction, perpendicular to this level curve. Now let's look at our algorithm. So x1 was obtained from x0 by subtracting learning rate times gradient at, I will use for nabla f, I will use just g notation. Then we calculate x2, which is x1 minus gradient and plus beta times x1 minus x0. If you look at this vector, so g1 is the blue vector, x1 minus x0 is this black vector. So now we want to add these two vectors. Do you remember how we add vectors? Vector A plus vector B. So first we should bring them to the common origin, and the sum is the diagonal of this parallelogram. So let's bring this vector, black vector, here. And the resulted vector, this sum, will look somewhere in this direction. And also these vectors, the black and blue one, they also scaled by some numbers smaller than 1. So the resulted vector won't be so large, it will be a small vector in the direction of this diagonal. So the new vector, the new point will be somewhere here. So this will be our x2. And you can see that this point is closer to the minimum than a point that we would choose just by gradient. So this term kind of adjusts the current gradient. Let's see. So I can actually continue. For example, if you look at the blue line, then it would go like in this direction, then in this direction, in this direction, and we should perform a lot of steps to reach the minimum. While this red line, so next step maybe would be somewhere here, then maybe somewhere here, and we would converge to the minimum along less noisy trajectory. So to understand this, let's express x1 minus x0 from the previous equation. It will be just negative alpha g0. Negative beta times alpha g0. And we can factor out alpha, and we will get g1 plus beta g0. If we look at the next iteration, x3 times beta x2 minus x1. But x2 minus x1 will be this negative alpha g1, negative beta alpha g0. So negative plus. And again, if we factor out alpha, we will get negative alpha g2 plus beta g1 plus beta squared g0. And now you can guess the general rule for update xt plus 1 equals xt minus alpha times the sum over from 0 to t beta power t minus I g I. So for example, if I is 0, we will get beta t times g0. If I is t, then we will get just gt. So this term is called exponential smoothing, because we always add the exponent of our constant beta. And why it's called smoothing? Because the impact of the gradient from like very uh, far step, like g0, will be multiplied by a very small constant, because if our power goes up, like beta power 10, the number will be negligibly small. So it means that for the update step, the main impact will be from the current gradient. Then we will get slight impact from previous gradient from the previous step. Then smaller impact from the gradient 2 steps before, and so on. So it means that if our current gradient direction is not optimal, it will be adjusted by previous gradients. And this term is called inertia. So that's why the name of this method has to do with inertia. And now, maybe 5, maybe less minutes of the derivation of this algorithm in math. Let's see. So, if I want to minimize a quadratic function, I used 1/2 just because when we take gradients, it will cancel out with 2. And in black, there's a gradient descent algorithm. Then, if my minimum point is x star, I can subtract from both sides of equation. It won't change nothing. And also at the minimum, the gradient is 0. So it means that a times x star plus b, which is the gradient of this linear function, quadratic function, will be 0. And it means that I can add this term to my equation. Then we denote these differences by epsilon, the error. And then this equation will take this form, that error is equal to the error on the previous step minus learning rate times matrix A times error. Or we can factor out error, and we will get this operator matrix, identity matrix minus alpha times A. And then we can substitute the same expression for EK and so on, and we will get the expression for the original choice of our approximation when we choose x0. So this will be the difference between x0 and the true minimum. And so this is the product. And I will denote this product as a polynomial of power k of our matrix A. And if we use the polynomial of just number, a lowercase, then this polynomial will look like this. Then if we use so-called spectral norm is the largest eigenvalue of the matrix, we can get this estimation of the error on the step k plus 1 through the matrix norm of the polynomial of our matrix A times the length of our original error. Because matrix A is symmetric, and the spectral norm is just the largest eigenvalue, then this norm can be estimated by the absolute value of our polynomial, where argument of the polynomial is in between the smallest and largest eigenvalue of our matrix. And now there is a mind-blowing idea. What is the polynomial which is the most close to zero on the interval between two numbers? So if we find a polynomial which is the smallest between all possible polynomials on the interval between lambda min and lambda max, then this polynomial depends on these coefficients, and these coefficients are our learning rate. Then we will find the most optimal learning rate alphas, because we will find the smallest upper bound for our error. And there is a polynomial which takes the smallest values on the interval, and this polynomial is known as Chebyshev polynomial. So I also played a little bit with code. So these are estimations for our error with function one minus, I used constant learning rate, alpha times x power 1, power 2, and so on. If our step is k, then it will be power k. And you can see that with increased number of iterations, this polynomial goes closer to zero. It means that our error also becomes small. That makes sense. Now let's plot Chebyshev polynomials. And it's a little bit hard to see here from, but for example, this blue line is the original polynomial of the first order. The green line is the, the orange line is the first polynomial, Chebyshev polynomial. And maybe it goes closer to the zero, like in absolute values, at least below. Then for k equals 2, we have green line and Chebyshev is red. And we're interested only in this interval, so don't look at because we're interested in polynomials only in our range between two numbers. Okay, it's just to illustrate that there are well-known polynomials that have the smallest value on interval. And the Chebyshev polynomials are defined on interval -1, 1, and this is the expression. The first polynomial is just constant, the second is just line x, then it's this recursive expression. There is also closed form expression for Chebyshev polynomials. So the next step is to shift our argument. So I shift my arguments to shift interval -1, 1 into interval between lambda min and lambda max. So for example, if a is 0, let's see, sorry, no, if a is lambda min, if a is lambda min, then we will get t of of 1. t of 1. If A is lambda max, we will get t of -1. So it's just shifting demonstration of the interval to adopt our Chebyshev polynomials for our interval. And also to get because if we use alpha 0, our polynomial should take value 1. So to get the value 1 at 0, we also normalize it by this constant. And after that, if you substitute, if you make the change of variable, so instead of x, you will use this argument, I skip the steps, you will get this recursive expression, which looks exactly as momentum. And finally, if we make the backward substitution, so we apply polynomial to error, then we write the error explicitly, you will get this method, gradient descent with inertia. And actually, one of the reasons why neural networks were not popular in the beginning of millennium is that stochastic gradient works slow. And this method, when we'll talk about computer vision next week, actually was used in all currently known convolutional neural network architectures. Okay, it was just a minute of kind of defending machine learning in front of math people. If you don't know math, it's unlikely you will come up with a new algorithm in machine learning, or you will understand why these formulas. Then it will look like, yeah, we just tried another term, like x t minus x t minus 1, and it worked. No, you you can, okay, of course, try different combinations of tricks, but of course, not all of them will work. You should have an intuition. And this intuition was only for convex functions. But then people use this for non-convex functions, neural networks are non-convex functions, and it performed better. Well, yes, there's no proof that this algorithm works for non-convex functions, but the intuition comes from the more simple functions. Okay, let's move to the next algorithm. I think it's just interesting, like how these algorithms were actually invented, introduced. And it wasn't far away. It was in 2010s. So next algorithm. Next algorithm is called adaptive gradient. Adaptive gradient. It's almost Adam, but Adam will be our fourth algorithm. So adaptive gradient, well, then we will talk about RSM prop, and then about Adam. So adaptive gradient. So if you think about sparse data, let's say you have one hot encoder, and then you will have the linear combination of almost all zeros. And one term will be non-zero. Then maybe it doesn't make sense to update all the components of your gradient at every step. So in this method, they propose to update our weights component-wise. So for different coordinates to use different learning rates. So pretty simple idea. So the formula looks as follows. Now, in addition to the time step, we will use also the index of the coordinate. So it's component-wise. Alpha over square root of one constant plus epsilon to avoid division by 0 and gradient. And now we take also the ith component of the gradient. And this constant v is calculated as the sum over previous gradients, g t I squared, g t g k I squared. So the idea here is that we will adjust, actually we will decrease, because alpha is divided by this v, we will decrease our learning rate, but for individual components in different amounts. Because maybe in this direction, we can perform longer step than in this direction of our loss function. And this term is the sum of gradients. For example, if we had 0 components and we had 0 gradients, then this v will be small. So it means that we won't decrease our learning rate for this component. On the other hand, for another component, this gradient was not 0, then we will increase this sum, so we will decrease the learning rate more for this specific component. So this is the idea of adaptive gradient. The next algorithm is known as RMS prop from root mean square. And it has exactly the same update formulas. Propagation prop. But a little bit different formula for this v constants. It will use the exponential smoothing that we saw in stochastic gradient descent with momentum. So it introduces another constant beta hyperparameter, beta times the previous value, plus 1 minus beta times the gradient at time t minus 1 I squared. So you can see that it's pretty the same, similar formula, but instead of adding the gradient from the previous step, we add this gradient multiplied by a constant smaller number smaller than 1. So kind of add this inertia. And it's interesting history about this method. You won't find any paper about this RMS probe. Did you hear about Geoffrey Hinton? He won Nobel Prize for machine learning last year. Do you know any popular people, scientists in AI, except me? So it was proposed by Geoffrey Hinton. Um, so this is the person who created first video course on machine learning. So he works at the University of Toronto, and as I mentioned, he won Nobel Prize last year. So it's the most popular guy in in this area. So and in this course, when he introduced optimization algorithms, he just said that okay, we can add the inertia term to the adaptive gradient. So he introduced a new method, which is now studied in every class, just during the lecture. So it wasn't published anywhere. It was just introduced during class. And I wish you guys to also, if you want to do research, to come with your ideas during class. And some people publish thousands of papers, but nobody reads these papers. And other people just introduce some adjustments to algorithm during class, and then everybody in the world cites this algorithm. And of course, it's also built in Torch. You can find momentum, you can find RMS probe, but as I mentioned last time, the first choice is Adam. So let's go to meet the last algorithm, Adam. Bless you. So this algorithm just combines previous algorithms, and the formulas look pretty similar. So it's exactly the same formula, but with additional parameter, which is changes mu Ti. And the formulas for update are as follows. So, the same formula for V, so I will just copy paste. And for mu, it's it uses another hyperparameter gamma, mu from the previous step, 1 minus gamma, and here's without square. So yeah, the only difference with the previous algorithm is that on one hand, we decrease learning rate. On the other hand, we control the magnitude of this decrement, of this decrease. So this mu, because if we decrease learning rate too much, then we won't update our parameters. And what do you think this name stands for? If you think it's the name of a person, it's not quite correct. Adaptive momentum. Adaptive momentum. Yes. So in the remaining time, I want to actually introduce you to Geoffrey Hinton. Let's see if I have his image. Oh, wait a second. One more thing before we meet with Geoffrey Hinton. So when we talk about mini batch, I want to give you a recommendation how to choose the size of batch. So um, um, if you want to estimate the variance, the deviation of our stochastic gradient from the full gradient, then the variance will be proportional to 1 over b. You remember 1 over b will go outside of the sum as 1 over b squared, but the sum of these terms will result in b over b squared, and variance will be approximately 1 over b. So the standard deviation will be approximately 1 over square root of b. If we plot this function, it will look as follows. So for stochastic gradient descent, batch size is 1. For batch, mini batch, it can be 100. And what can you see from this plot? Where's the greater difference between batch size 1 and batch size 2, or between batch size 100 and batch size 101? Of course, of course. So it means that maybe we don't want to use a very large batch, because then the difference won't be significant, but the computational time, we will spend more computational resources to process larger batch. So the recommendation is to use a batch size between 1 and 100, because larger batch size kind of doesn't improve the deviation from the full batch, or as much data as you can fit in your GPU card, because for images, for example, you can fit maybe 8 images on GPU card. Then your batch size will be 8. So fit the memory. Because maybe you want to use batch size of 100, but you will get the error out of memory. Okay. So Geoffrey Hinton. Let's see. Let's think how connected AI, machine learning, and deep learning, while I'm looking for the image. What is the connection between AI, ML, and DL? Oh, here it is. Huh? Yeah, so this is how the first course on machine learning looks like. Mm. So what is the definition of machine learning? Remember, on the first lecture, I said we'll give definition somewhere later in class when we will go through through the material. So what is the definition of AI or ML and how they are related? For example, you know, if somebody will ask you, what did you study in AI class? What did you study in? For example, if you took calculus 2, you can say, I studied the convergence of the series. So what is the relation between AI and ML? You don't know? Um, so the common diagram looks as follows. Let's see. Mm. So this is the typical diagram how people represent the connection between AI, ML, and DL. But nowadays this diagram should look differently. Nowadays it should look like that. So this is ML, and this is DL, because almost all models now are using neural networks. So every time when I see this diagram, I don't understand why people don't visualize this as follows, because this is the current state of the things. But what is that AI? What is the artificial intelligence or machine learning model? So this is the model that can perform a given task, for example, handwritten text recognition, with the same accuracy as human beings or better. So this is the common understanding of AI or ML algorithm. But there is a missing component. If you think about some machines that, for example, drill the holes in the earth for the electric poles, is it they do this better than me? They do this better than people. Is it AI machine or not? No. So the definition that I gave in the beginning is not quite correct. There is a missing component that our algorithms, they are not programmed, they deterministically. They can update their behavior based on the data. So the second component is that these algorithms are using data. And the conventional AI, which was appeared in 60s, didn't make nice progress till 90s. So researchers missed the funds, and they decided to use another name, machine learning. So it's a new term in new science, and it's not compromised by AI that didn't have much success except just some database learning search. Yeah, and currently deep learning is the main tool, and this is what we actually will work till the end of the class. Okay, that's it for today. And yeah, we will continue deep learning next week.